Now that you've seen some examples of cosets, let's prove some of their properties. And as a side perk, we're going to get one of the most important theorems of group theory, namely Lagrange's theorem. So I'm going to fix notation for some of the results we're going to be talking about. So let G be a group and H will be a subgroup of G. And the first lemma is the following. Suppose I take two elements of big G, I call them G and G prime, then you know that the coset GH and the coset G prime of H may be the same coset, like in some of the examples, or maybe are different cosets. So one question is, can I somehow recognize by looking at the elements G and G prime if they're going to give me the same coset or not? So the claim is that the G and G prime give you the same coset, so GH is equal to G prime H, if and only if G inverse G prime is an element of H. Let's prove this. So because it's an if and only if statement, I need to prove two directions, of course. So let's first suppose that the cosets are equal. What does that mean? Then G times the identity, look, this is G times something in H, right? This is an H, belongs to the coset G prime H. Right? Everything in this coset belongs to that coset if the cosets are equal. What's a particular thing that's in this coset? It's G times something in H. So I can take G times the identity in H. G times identity is definitely an element of GH, so it must be an element of G prime H. So what does it mean to be here? That means I can write GE as G prime times some element. I think I want to call it H0. No, actually it doesn't matter. Some H for some H. In H. What do I want to prove? I want to prove something about G inverse G prime. So I'm going to multiply both sides here on the left by G inverse. So what do I get? Hence G inverse G, which is the same as E, is equal to G inverse G prime H. So now I'm going to multiply both sides on the right by H inverse. And what do we get? I get that H inverse is equal to G inverse G prime. Okay, this H inverse cancels this H. Oh, but this is an H. H is a group. Big H is a group. So if little h is in big H, then the inverse of little h is also in H. So what does that mean? That means that G inverse G is in H as desired. So G inverse G prime is in H as desired. Okay, now we need to prove the converse. So conversely, suppose that G inverse G prime, G inverse G prime is in H. What does that mean? i.e. G inverse G prime is equal to some H0 is in H, so it's equal to some element H0 of H. So if I multiply now both sides on the left by G, I get that G prime, so G times G inverse cancel, so I just get G prime, is equal to G H0. Okay. What am I trying to prove? I'm trying to prove that these two cosets are equal, and to prove that two sets are equal, right? These are sets. I need to prove that the left one is contained in the right one, and then also the opposite, namely that the right one is contained in the left one. So now I want to prove that the left one is contained in the right one. So how does an arbitrary element of GH look like? Well, so let H be an arbitrary element of H, of big H. Then, if I look at G prime H, I get, so multiply both sides by H, I get GH0H. All right, both H0 and H are in H, so H is a group, so this thing is in H. So what have I shown? That this element G prime H can be written as G times something in H. So that means this thing here is contained in GH. Okay, but little h was an arbitrary element of H, which means G prime times any element of H. So this belongs here, right? It's not contained, belongs. So G prime times any element of big H is contained in GH. Hence, G prime H is contained in GH. Right? Just to summarize again, to prove that, I need to show that every element here lies there. How does an arbitrary element of this set look like? It looks like G prime times some arbitrary element of big H. So it looks like that. And we just showed that anything that looks like that can be written as G times something in H. So it means that it lies in GH. Okay? So we proved this containment. So I should change the color coding here. And actually, the orange argument serves to prove this containment. So now we want to prove the opposite containment. So I guess the opposite one, denote it in blue. So also, let's look at this. I have that equality here. So also, if I'm trying to now express, previously I expressed G prime as G by G and H0, and now I want to express G. So I'm going to multiply on the left again by G. So, okay, let's just say maybe not start with this equality, but with this one here. This one. So from this, if I multiply both sides on the right by H0 inverse, I get that G is equal to G prime H0 inverse. Okay? G H0 H0 inverse just gives me G, and on the other side I get G H0 inverse. So I get that. Okay, so now I just exactly repeat this last line. I'm just going to rewrite it almost verbatim. So let H be an arbitrary element of big H. Then I multiply both sides on the right by little h. GH is equal to G prime H0 inverse H. Again, I notice that this thing is in H. So that means GH belongs to G prime H. Because H was arbitrary, this means that I get GH contained in G prime H. So what do I have? Do I have the two containment I wanted to? Here is the G prime H is inside GH, and here GH is inside G prime of H. So GH is equal to G prime H. All right, so that gives us one way to see if two cosets are equal. If two cosets are equal, GH is equal to G prime H if G inverse G prime belongs to H. Now this statement is about left cosets, but you can write a similar statement, an analogous statement about right coset. And then you will see there'll be something slightly different where you put inverse and where you don't, right? Here is G inverse G prime, so there might be something different when you compare right cosets. I'll leave it to you as an exercise to formulate this lemma and prove it. So the lemma will be that G prime be in G, then HG is equal to HG prime if and only if something is in H. I'll leave it to you. Okay. So let's get a corollary from this. From this lemma. The following one. So corollary, I call corollary 2. H is equal to GH if and only if G is in H. We've seen this already in examples. When I took an element of H and I did that element times H, I actually always got H. So now this corollary tells me that that's always true. How does the corollary follow from the lemma? So we just need to take G prime equal to the identity in lemma 1. Okay, really? Let's see. If I take G prime as the identity in lemma 1, then lemma 1 tells me that GH is equal to EH. Oh, but that's just H. Okay, so it says GH is equal to H if and only if G inverse is in H. But if G inverse is in H, H is a group, so that also means that G is in H. So corollary 2 just follows exactly from this line. Okay. What's interesting, another thing that maybe you have noticed when we did examples, was that all the cosets we came up with for a given group and a subgroup always had the same number of elements. So this in fact is always true. So that will be our proposition. So proposition 3. And we stated, I want this thing to even hold for infinite sets. So let's state it in the following way. So let G and G prime be in G. Then the map phi from the coset GH to the coset G prime H given by phi of, well, how does an arbitrary element of GH look like? It's little g times something in H. And I'm supposed to now get something that looks like G prime times something in H. I'm just going to use the same H. So that's just a map. This element clearly lies in this coset, and this element clearly lies in that coset. So it is a map from here to here. Is it a nice map? Yes, it's a bijection. One thing that maybe you're wondering by now is, are cosets the same as subgroups? One coset is the coset H. So H is a subgroup, so H by itself is also a coset, right? It's E times H, so it's a coset. But that is the only coset that is a subgroup. You will see in a moment that cosets are either equal or disjoint. So that means if I take another coset other than H, then it will not have the identity inside it. So it wouldn't be a subgroup. So H is actually the only coset that is a subgroup. So the other cosets are just sets. They're just subsets of G, right? All of them just lie as subsets of G. So I'm saying that if you take that map, then it's actually a bijection. So let's prove this. Is actually very easy to prove. So note that phi, I'm not even going to mention that it's well defined. I mean, clearly the image of GH is G prime H, so it does lie in the correct coset. But note that phi is surjective. It's clearly surjective. Essentially, by definition, what do you need to do to show that some map is surjective? You need to show that you can get every element here as phi of something. But how does an arbitrary element of G prime H look like? It's G prime times some little h. So I have to now find an element that maps to G prime times H. Well, GH. So it's clearly surjective. Is it injective? Furthermore, if phi of GH is equal to phi of G H prime for some H prime in H, then, alright, what's phi of GH? That's G prime H. What's phi of GH prime? That's G prime H prime. So, H is equal to H prime. Because I can just multiply both sides of this equality by G inverse on the left, and I get H is equal to H prime. Hence, phi is injective. So indeed, this map is a bijection. This tells me, in particular, that any two cosets have the same size. So, corollary for any two cosets. Oh, maybe let's just write it precisely. So let G and G prime be in G, then G H and G prime H have the same cardinality. Cardinality makes even sense for infinite sets, but we're not going to worry about this. So in particular, when they're finite, if GH is finite, so is G prime H, and they have the same number of elements. Because bijection is possible only between two sets that have the same number of elements. Okay, so now we are ready to prove this last property of cosets that I kept talking about, namely that they are either equal or disjoint. So that's going to be our proposition 5. Let G prime be in G, then GH is equal to G prime H, or their intersection is the empty set. Only these two possibilities can occur. Let's prove it. How do you prove a statement which has a conclusion of the form either something happens or something else happens? You just assume that one of these things doesn't happen and then show that the other must happen. So let's assume that they have a non-trivial intersection. So suppose GH intersected with G prime H is non-empty, and then we'll show that if this happens, then the two cosets are actually equal. Well, if the intersection is non-empty, then there is some element that lies in the intersection. So let X be in the intersection. So that means X lies in this coset, so I can write it as GH0. But it also lies in this coset, so I can write it as G prime H0 prime. for some H0, H0 prime in H. Hence, I am just going to concentrate on this equality here, and actually now ignore the x. The x is sort of a red herring here. It is necessary only to make that equality true. Otherwise, I'm not going to need the x anymore. And I'm going to manipulate this, because how do you show that two cosets are equal? Remember, I have to show, in this case, that G inverse G prime belongs to H. All right, so let's do this. So I'm going to multiply. So I want to get G inverse and G prime by itself. So I'm going to multiply on the left by G inverse. So I get H0 is equal to G inverse G prime H0 prime. Okay, I want to get G inverse and G prime by itself. So now I'm going to multiply on the right by H0 prime inverse. So if I do that, so I get that H0 prime inverse is equal to G inverse G prime. Aha, okay. So G inverse G prime is equal to that, but this is an element of H. So G inverse G prime belongs to H. Hence, I can conclude that GH is equal to G prime H, and that was, I guess for us, that was lemma 1. By lemma 1. And this finishes the proof. So indeed, two cosets cannot have, if they're not the same coset, they cannot have any element in common. Okay, let's make a we can now prove Lagrange's theorem. So theorem, Lagrange's theorem. Let G be a finite group. And let H be a subgroup of G. Then the order of H divides the order of G. All right? This is actually quite important. So if you have a group of order 6, you know that it can possibly only have subgroups of order 1, 2, 3, and 6. No subgroup of order 4, no subgroup of order 5, because 4 and 5 do not divide 6. Right? And more applications than that, but let's prove it. All right, so I'm going to prove it in words, and then next to it I'm going to sort of be drawing a picture of what's going on. So here on the picture is a group G. So in my case, it's going to have like 6 elements. So that would be group G. And inside it, there is a subgroup, namely H. Okay, this is a subgroup H. And now what I'm going to do is I'm going to look at cosets of H. So I'm just going to look at, all the possible GHs as G runs through G. And of course, every element of G is in one of those cosets, because I can always write G as G times E. So this belongs to GH. So every element in G is in some coset. So let's just write this as first thing. Note, every element G in G belongs to some coset. for example, to GH. Okay? So if I just keep changing this G, running over the entire group G, like here, I would get 6 cosets. But you know that some of the cosets may be the same. So I'm not going to count twice the cosets that are the same. So let's say this is H, right? Maybe here's another coset. Maybe that's like, I don't know, G2H. So this will be like G1H, where the G is maybe the identity. And then the last coset will be like here, G3H. Okay? So let G1H, G2H, GNH be all the distinct cosets of H, right? So even though I can, like in this case, use 6 different G's to produce cosets, I only get 3 different ones, right? I would get repetition if I used all 6 of them. So I'm only going to look at the different ones. So in this case, it'll be like G1H, G2H, and G3H. So we know by the previous proposition, we know they're all disjoint. So all these cosets are disjoint. And of the same size, namely the order of H. So I can write G as G1H union G2H union ... union GNH. And so this union exhausts H. Each of these guys have size H, size H. I don't say orders because they're not groups. And they're all disjoint. So I say that the size of G is n times the size of H, right? Each of these has size of H and there are n of them. So it's n times the size of H. Hence, H must divide, the order of H must divide the order of G. And we get Lagrange's theorem. So that finishes the proof.